So we spent a bunch of time yesterday talking about the origin of the constant acceleration kinematics equations, and I broke things down into, I think, 3 different categories of equations. They're basic definitions, and then kind of basic facts about constant acceleration. And those 2 categories all deal with either the v-average, the average velocity during a process, a simple constant acceleration process, or the delta v. And then there were those 2 other equations that are usually used when the first categories don't give you anything obvious right away. So one of the auxiliary equations was what I call the v-squared equation. So I want to talk about that one first. And hey, there we are. Something weird is happening. It's not getting mouse clicks. Let's stop sharing the screen and see if it gets mouse clicks. No. OneNote stopped working. Unmute the microphone. Okay, I think technical difficulties are handled now. All right, sorry for that delay. So here is the v-squared equation. And I think that this is kind of an underappreciated, underutilized equation in kinematics analysis. What it's going to get us is a way to deal with getting from point A to point E in our example problem from last week. from yesterday. Yeah, it's not that long ago. So here was A, and our object is going up and comes back down and slams into the ground at point E. And what we know is the delta Y. That's the key fact that tells us which dash along this parabolic curve point E is actually located at. And we also know that V initial in the Y direction is what we would call V sub A is plus 20 meters per second. And of course, one of the things I said about free fall is that the acceleration is negative 9.8 meters per second squared. So that's our given information. And if we try to use the delta Y equation, the one with the 1/2 AT squared term in it, then we end up trying to solve for time, which I think is a little bit of a pain, and I'd rather avoid it because I tend to make mistakes when I try to solve a quadratic equation. So the V squared equation gives us a way to make kind of an end run around solving the quadratic equation. So when we think about our given information here, I wrote the V squared equation in terms of x because generically we talk about motion in the x direction. In our specific example, we're moving vertically up and down, so I'm calling everything y's. But we have enough information to fill in basically the entire right-hand side of the equation. We know the initial conditions, we know the acceleration during the process, and we know the displacement, which is the key to figuring out exactly where along the process we stop at point E. So when we plug this stuff in, we get VE squared is plus 20 squared plus 2 times negative 9.8 times negative 50. So the acceleration is negative and the displacement is negative. And this is because gravity points down and the object ends up below its starting point. So this turns into 400. And this turns into 2 times 50 is 100 times 9.8 is 980. So this is 1380. And the units of that are meters squared per second squared. You could get the units by looking at the V squared at the beginning. Those were meters per second, and the quantity is squared. You could get the units by looking at the multiplication of acceleration with displacement, because the acceleration is meters per second squared, and then we're multiplying more meters. You can only add terms if they have the same units, and they do have the same units. So we end up with that, which means that our V at point E is equal to the square root of that, which I don't happen to have written down. $37.1. And at this point, we have to make a physics decision. The math of the V squared equation, if we're solving for V, doesn't tell us whether that velocity is positive or negative, because the velocity appears in the equation as a V squared. So either the positive solution or the negative solution will actually solve the equation. it's kind of like the dilemma you come up with the quadratic equation, where if you use the quadratic formula, there's negative b plus or minus the square root of 4ac, or negative b plus or minus the square root of b squared minus 4ac. So you have to take that square root and consider adding or subtracting that number in the and the formula. It's kind of a little weird. You have to actually try both possibilities, think about what they mean, decide which one's more applicable to your situation. And that can not always be obvious. So you get two results. Sometimes one result is negative and the other's positive, and then you can think, oh, I obviously want the positive answer. But sometimes you get two positive answers, and you have to think, do I want the first one or the second one? Well, here, I think it's a lot easier to choose whether you want the positive result or the negative result, because this thing is a velocity. And we know what a positive velocity means. A positive velocity means moving in the positive direction. And we chose up as the positive direction. We started at plus 50, we worked our way up plus 20.1 more than that. And we're back down to 0 at this point, y equals 0. So we know what a positive velocity means. So we can make a conscious, intelligent, and fairly straightforward choice as to whether to use the plus or the minus here. So which are we going to use? The minus, because it's hitting the ground. It's heading downwards at the moment it touches. Now, don't think this thing hits the ground, the final velocity is 0. That is a different process. We're trying to analyze constant acceleration processes. So the act of throwing is one process. The object flying through the air is the process we are concentrating on. The act of landing on the ground is a completely separate thing. And we don't really have the tools to figure out exactly how the process of landing is going to occur yet. So we're going to think about that after we deal with forces and energy and momentum. Then we can start to think about how an object hits the ground. But for now, we can get to the point where the object barely touches at our final point of our analysis. So VE is equal to minus 37.1 meters per second. And we choose the minus because the object was moving downwards. Now, can you think of a case where you do projectile motion and choose a final velocity that's positive? Any ideas for choosing a final velocity that's positive? Well, a balloon is kind of weird because I think of a balloon as being very large, but also pushed around by the air. And we're trying to concentrate on a simple process of free fall where gravity is the only influence on our object. Balloons are definitely influenced by something other than gravity. So we want pure projectile motion, an object just flying through the air, nice and simple like, but at the moment the free fall ends, or at the moment our analysis ends, our velocity is positive. Can you think of anything that was supposed to be it when an object hits a ceiling? So it is a different situation, but it's certainly a possible situation to have the final velocity be positive. And like I showed, that would involve the object moving upward and getting to some point that you care about. Okay, so this opens everything up for point E, because now we can say we're still dealing with the process of going from point A to point E. We have our delta Vy is V at E minus V at A. And we just figured out the V at E is minus 37.1 minus, and I'm going to flip back to the other page, look up our velocity at point A. Our velocity at point A was plus 20, so we can go back over here. So our delta V for this process is negative 57.1 meters per second. We started with positive 20 meters per second, and we're losing 57.1 meters per second, which means now we're definitely in negative territory, negative 37.1. And I think that finding the delta V actually opens everything. That should be your goal in every kinematics analysis. If you can't figure out exactly what to solve for, which equations to try to use, try to find delta V. Because if you can find delta V, it's closely linked with the position of the object, and it's also closely linked with the timing of the scenario. And how is it linked with the timing? Well, we know delta Vy is equal to Ay delta t. Acceleration causes velocity change. So now we know that negative 57.1 is equal to negative 9.8 times delta t. So delta t is equal to divide that by 9. Whoops, I forgot to add the 20. 5.83 seconds. So now we can go back into our table and put in 5.83 and negative 37.1 and put a little star here. And make note that those things were added to the OneNote table after lecture today in lecture 3. So we filled in almost our entire table of knowledge about this scenario. The only one we haven't dealt with is point D, which was a well-defined amount of time. So let's go ahead and do that real quick. Process A to D, delta t is equal to 5.0 seconds. So I like to use my delta V equation. So delta Vy is equal to Ay delta t. I was using blue for this kind of stuff. Is negative 9.8 times 5.0 is equal to negative 49 meters per second. And then how do I use that? Delta Vy is equal to V final minus V initial. That's what delta is always equal to. And then negative 49 is equal to V at point D minus 20 so negative 29 meters per second is equal to V at point D. So now I can go back and fill in, apparently in green, negative 29 with a little star here. And we're left with only one thing to find, the displacement. And we actually have two ways of finding the displacement. One is the 1/2 AT squared equation, which is perfectly easy to use if you know the time. So I'll just use that. Delta y is VIY delta t plus 1/2 AY delta t squared equals, let's see, the initial is, what process are we doing? We're doing process from point A. So the initial is the A velocity, which was plus 20. The delta t is known, that's 5.0 seconds, plus 1/2 times negative 9.8 times 5.0 seconds squared. And it's an equation that is, like I said, pretty straightforward. This is 100 plus 0.5 times 9.8 times 5 squared is negative 122.5. So that's negative 22.5 meters. And that is delta y is final minus initial. So this is y at point D minus y at point A. Negative 22.5 is equal to y at D is what we don't know. Y at A was 50. So y at D is equal to 27.5 meters. And then we fill in that last thing in the table. $27.5. So my process for dealing with kinematics is this constant back and forth between thinking about instants in time. What do I know about an instant in time? How am I going to anchor it to another instant in time? What's the process used to get me from one time instant to another? And then the equations that get me from one instant in time to another are the definitions of the delta and the V average, the basic fact about the delta and the V average that are true during constant acceleration, and these two equations, which the 1/2 AT squared equation and the V squared equation, which are useful for preventing me from having to go through a lot of algebra manipulation during my process of solving. Does anybody have any questions, comments about this example? Absolutely. So let's look back at the equation sheet, which is not there. It's here. So here's the section of kinematics definitions. And then here's the line for constant acceleration. And here's the 1/2 AT squared equation. And then next to it is the V squared equation. And both of these are really useful. Now, if you're in a situation of projectile motion or free fall, we call it free fall basically when an object is moving straight up and down, and we call it projectile motion when the object is moving sideways. Our basic assumptions about projectile motion and free fall are on this line. We assume that in the x direction, there's no acceleration, and we'll talk about that on Monday or Tuesday. And we assume in the y direction that the acceleration is negative 9.8. which is also called negative g. So that acceleration appears all over the kinematics equations. All right. Now, one thing I would like to point out is that I did post homework 2 there, and I set homework 2 to be due next Sunday night, but remember, we have our test next Thursday. And all these questions that are on homework 2 are covered in the test. So you should probably not wait until after the test to do the homework. Otherwise, you'll get the test to be like, oh, I probably should have practiced that. And then you'll get to the homework and you'll be like, oh, well, if I had done that before the test, my test would have been easy. So that is available for you. And homework 1 has been available since Tuesday. You've had a couple days to look at it. Hopefully you have looked at it. I think tonight is the deadline for getting bonus points for working on homework 1 questions. So with that, does anybody have anything you'd like me to talk about from homework 1? Any issues you're having trying to understand the situation? I have it over here on my other screen so I can look things up as necessary.
Velocity.
What about instantaneous velocity?
Question 12 said T equals 18.9. Question 12, very bottom says master.
Yeah. Okay, so I like to think about equations for processes, but very often we want to think about arbitrary points in time. So if we have, say, a position graph, so this is going to be x versus t. And we can I'll draw a parabola because accelerations turn out to be parabolic. So we can still think about our process equations, our basic kinematic process equations, and apply them to this situation. And think about what it makes the function of time look like. So the process we can think about is the process of getting from the origin to an arbitrary time t. And our delta t is basically the same thing as plane t, because the further along the axis we go, the bigger the delta t is, and they are exactly equal to each other. Our delta x is kind of x minus what I call x naught. That is this value here. So the little subscript 0, I pronounce using the British pronunciation naught for nothing. And it basically stands for the x value when t happens to equal 0. And what we know is delta x is equal to v initial x delta t plus 1/2 a sub x delta t squared. That's our basic kinematics equation for a single constant acceleration process. So what does that look like when we use delta t equals t and delta x equals x minus x naught? This turns into x minus x naught. This we usually call v naught, sometimes v naught x. The delta t's turn into regular t's. Oops, I shouldn't be writing delta t anymore. I just said that. And then there's a 1/2 at squared at the end. Now, if we just solve for x, x is x naught plus v naught t plus 1/2 a t squared. I guess I should have little subscript x's on everything that is directional. So I would call this a template equation for the position of an object. And it is a quadratic equation. It's the equation of a parabola. And these things here are constants. And when you record the position of an object, such as we do in lab, such as is given in this particular example, so this is example 2.3. Sometimes you're just given x is equal to something like 38 plus 3.3 t plus 0.8 t squared. So what we do here is we just match term by term between the specific numerical equation that we're given and the more generic template equation that we're given. So this thing here, that's x naught. The 3.3, that's v naught x. And this 0.8 is 1/2 of a. I've come to just calling that number half a because then I can remember, usually I write it out a, but I remember double. So that is how a measured equation relates to our, hey, how's it going? I have. Well, yesterday we had a lot of trouble with this projector. Yeah, it seems like once the room gets warm, it turns off. All right. So we typically take a 10-minute break during the middle of our class, and I think this is a perfectly good time to take our break. So, hey. Unmute. Oh yeah, my computer has a mute button on it. It doesn't work though. Like, maybe my mute button only works locally. All right. So we figured out how to extract parameters from the x equation, and then we can also deal with velocities. Wait a second. I want that. There we go. So I can think of two ways to deal with velocities. One is that v is equal to dx by dt. So if you know x as a function of time, you can literally just take its derivative. So in that case, we would look at that thing, take its derivative, and get 3.3 plus 1.6 t. And then method 2 would involve our delta v equation. Delta v is a delta t. And our delta v is the v at an arbitrary time, which we often represent as just a plain v by itself, minus the v at time t equals 0. And that's represented by a v with a subscript 0. And this is a times t. So that gives us v is equal to v naught plus a t. So we would plug in our parameters from above. V is equal to, our v naught was 3.3 plus our a from above was 1.6 times t. And notice the two methods give the exact same functional form for the velocity. I mean, if you have two methods of doing the same thing, they better get the same result. So the three questions they ask you: determine the displacement of the particle from t equals 9 to 20. So you can take the x equation, plug in t equals 9, get a result, plug in t equals 20, get a result, subtract final minus initial. So the result from 20 minus the result from 9. That'll give you the displacement. It asks you to calculate the average velocity from t equals 9 to 20. And average velocity, you could get two ways. You could do v initial and v final and take their average, because this is a constant acceleration process. Or you could do delta t. In the previous question, you just calculated delta x. You might as well just do delta x over delta t. And the last question says find the instantaneous velocity at a particular time. You just plug that time in here, because that's what that function gives you, is the actual velocity at a particular instant in time. So there's lots of symbols we use for different instantaneous velocities. The VI and VF that I've been using a lot stand for the instantaneous velocity at the initial moment or the instantaneous velocity at the final moment. You can really use any subscript label you want, as long as it tells you as long as it communicates to you what moment you care about. And then there are a couple of kinds of velocities that are not instantaneous velocities. They're velocities for a process. And that's the V average, which is technically delta x over delta t. And the delta V, which is V final minus V initial. So the first group of things is all different kinds of instantaneous velocity that we might care about. And then the V average and the delta V, you have to have a well-defined process that you're thinking about at the moment. Usually, I define my process by writing it as a heading, as a label. I say, I'm going to analyze process A to E, or A to B, or A to C. And then under that heading, when I talk about V average, I mean the average velocity between moment A and moment B, or between the moment a projectile is launched and the moment when it lands. That's the average velocity. So that's a little bit of the notation that sometimes isn't said so explicitly and ends up confusing students for some reason or another. I want to talk about a couple of different special cases. And one of them is the idea of stopping distance. This is something we care about. We drive around. Occasionally, things jump out in the road in front of us. Occasionally, other vehicles stop in the road in front of us. So it might be important to understand the relationship between how fast you're driving and how much distance it takes you to stop. And the easiest way to think about stopping distance is to look at the v-squared equation. So we're talking v final squared equals v initial squared plus 2a delta x. And if we're in a process of stopping, then our v final should be 0. At least if we successfully stop, our v final is going to be 0. And we can kind of move this around a little bit and say minus vi squared is equal to 2a delta x. Now, in this deceptively simple equation, there's an explicit minus sign on the left-hand side. That's part of the equation. It happened because I subtracted vi squared from both sides. Now, if the left side of the equation is negative, and it is because we see the minus sign, and the vi is squared, so it can't be negative to cancel out the minus sign. So the left side is negative. That means the right-hand side of the equation also has to be negative. Otherwise, it's not an equation. And we don't see an explicit minus sign on the right-hand side. So there must be a negative sign hiding inside one of those variables, an implicit minus sign. And we don't know right away whether it is in the acceleration or in the delta x, but it must be in one or the other. So either a sub x or delta x is negative. And the other one is positive. So if you have an object that is traveling in the plus direction, so object is moving to the right, and you want to stop, it takes a negative acceleration to make it stop. And we're going to talk after exam 1 about what causes acceleration. Acceleration is caused by force. You have something that is moving to the right. You want it to stop. You have to push toward the left at it. That's the negative acceleration. On the other hand, if you have an object that is moving in the negative direction, then it takes a positive acceleration to make it stop. As long as the acceleration is opposite to the motion, you're going to make your object slow down, maybe stop. Now, when I use this in a practical calculation, I usually just say v squared is equal to 2a delta x. And I run the equation for all magnitudes because I can think consciously and carefully about whether certain quantities are supposed to be plus or minus. I'm using the equation to find out the magnitude, the strength of the acceleration, or the strength of the delta x. And when I use this equation, the stopping distance is clearly proportional to v squared. So if you compare two scenarios and one has twice as much velocity as the other, the one with twice as much velocity is going to take 4 times as much stopping distance. Now, I've made an assumption when I said that. I kind of assumed that these two situations had similar accelerations. And I guess I could summarize that by saying that if you have a particular car on a given road, then it has a certain amount of acceleration that it can achieve. That's not saying it's always driving around with that acceleration. That's just like the maximum acceleration that it can have. Maybe I should put the word max after that. So if I give you a question about stopping distance and think about two situations with different velocities, you should assume that they have the same acceleration and that the x is the only thing on the right-hand side of the equation that's actually changing. So let's do an example. V initial is 30 meters per second. So that's about highway speed. And A is equal to 5 meters per second squared. And 5 meters per second squared is an approximate acceleration I'm making up for a car driving down a road. depending on the road conditions, depending on how much dirt and dust is on the road, you could get up to a maximum of around maybe 8 meters per second squared of acceleration. Race cars have softer tires that are designed to get better grip on the road, so they might be able to get an acceleration up to like 10 or so meters per second squared. If the road is wet and hydroplaning is a problem, or I don't know if you've noticed, but when it rains, after it hasn't rained for a long time, the rain tends to float all the oil and grime off of the road and it gets super slippery. That might give you an acceleration as low as like 1 or 1/2 of a meter per second squared. And if the road is icy, there are places where ice comes down from the sky. I know those places aren't here usually, but it does happen. That makes the grip even less, and then the acceleration maximum might be as low as like 0.2 meters per second squared. But this gives us a way to easily calculate the stopping distance. So v squared is 2a delta x. So 30 squared is 2 times 5 times delta x. So delta x is equal to 90 meters, which is something like 300 feet, which is pretty long distance, a little less than 300 feet. So that's why we like to have lower speed limits in school zones, because we typically don't want cars to be running over our children. They're idiots and they'll run out in the middle of the road once in a while for no particular reason. So if we rerun this, with VI is only 10 meters per second, then we get 10 squared is 2 times 5 delta x. And we get delta x is equal to 10 meters, which is only about 32 feet, which gives the driver a much better chance of actually stopping in time. And 10 meters per second is roughly 20 miles per hour. I think it's like 21 and a half miles an hour. So this factor of 3 change in the velocity caused a factor of 9 change in the actual achievable stopping distance. All right. What else should I talk about in order to help you with kinematics? What's up?
I have a question from the ones.
Okay.
11B, it has to do with the distance traveled and there's like 7 intervals.
Yeah. So I think there's only one L in that word. I think I've been spelling it wrong in the last 2 days. So the topic is kind of distance traveled during a constant acceleration process. And the basic principle is if you have one directional motion, the distance traveled is the absolute value of the displacement. Now, in one directional motion, there are only two possible directions for the motion. I'm sorry, in one dimensional motion, you have two possible directions. So if you can move along the x-axis, you could move forward and backwards. So there's the possibility of having a reversal of direction. What you need to do is break the process into stages. So what do I mean by that? I can explain myself best with a graph. So let's do x versus t. And let's say that we have a process that's a parabola. And we're trying to find the distance traveled from t equals 0 to this t sub final here. And what we need to make note of is that there's a moment here, t sub a, and at that moment, the direction reverses. So, like I said, we have to break our process into stages. We can go 0 to t sub a. That's one process. And then t sub a to t final. That's our second process. So our delta x is x a minus the initial x. And for our other process, delta x is equal to x final minus x a. And if you're calculating total displacement, then you would just literally add these things. The problem is we're calculating distance, so we have to take the absolute value of them. And that's going to flip the one that's in the reverse direction. So what you have to do is my mouse and my pen were fighting each other. You have to find that turnaround point. There's lots of ways of thinking about that. We did it for our point B for the projectile motion, where I launched a projectile up with an initial velocity of 20, and we said at point B at the top, the y velocity was 0. And that's a perfectly good way of finding that point. You're basically trying to maximize the x value. So how do you find a maximum? You take its derivative, set it equal to 0. The derivative is the velocity. So you might need to look at the velocity graph, or at least think about the velocity graph. And if this is a graph of v sub x versus t, let's figure out what this should look like. There should be positive velocity at the beginning because we have an upslope, and it should get less and less and less and less and less. And at this point, at t sub a, so let's drop that down to our other graph. At t sub a, the velocity should be 0. And then from that point on, the velocity starts to be negative, and it gets worse and worse, well, stronger and stronger and stronger. So our velocity graph actually is going to look like this. So you probably want to use the initial velocity and the acceleration to figure out what time this happens at. then you can figure out where this final point is, so that you can calculate a displacement to get to point A and a displacement to get from point A to the end. And that's why for questions for parts C and D of that question, you have an object with a given positive acceleration. It has a positive final velocity. For part C, it says the initial velocity is negative. So it's basically shooting downwards on the x graph and then coming back up at the end. It has a turnaround point somewhere in the middle. So you need to find that peak and figure out the distance it travels to get to the peak, and then the distance it travels to get from that peak to the final point. And our basic kinematics equations work great for this situation. The definition of V average, the fact about V average, the definition of delta V, and the fact about delta V. They work great for this. But the 1/2 AT squared equation works great also. Because this functional form is V initial t plus 1/2 AT squared. As I drew it, this acceleration happens to be negative. But in the homework question 11, it is positive. So you would say something like delta S is absolute value of delta X. Calculate them separately, take their absolute values, and then add them. Okay? Any other questions about the homework? Well, I would like to kind of give you a kickstart on the very last question, the dropping the rock down a well question, because it seems to tend to be a challenging question for the Physics 2425 students. So, so let's think about this. What we know is the acceleration is negative 9.8 meters per second squared. V initial is equal to 0. And then we have this fact V sound is given. And I'm going to use I guess 336 is what's on my screen as my speed of sound. And they give us a time for a process. And in my case, its delta t is 2.93 seconds. But the process they give us the time for is not a simple constant acceleration process. The process they give us the time for is a two-stage process. There is a falling of an object with an initial velocity of 0 and an acceleration of 9.8 meters per second squared. And then there is a process of the sound coming back and the echo gets to our ears. That's a constant velocity process for the second half. So this is kind of like an A to C process. So we have the process of dropping, and our object is moving slow, faster, faster, faster. And then the object hits the bottom, splash, crash, however you want to think about it. And then we have the sound coming back. And the echo happens, and that's my point C. So during the drop, we want to be thinking about the relationship between, so this distance here is, I'm going to call H for the height of the top of the well from the bottom. H for the depth of the well. Perfectly good variable for that. And for A to B, as it turns out, the easiest equation to use is the delta Y equation. And the reason is that the delta Y is minus the height of the initial position. And then this is 1/2 minus g t squared. Or h is 1/2 g t squared. Now this happens frequently enough that I decided just to extract it from the 1/2 at squared equation, and I wrote it down here as a special case. That's the relationship between the height of holding something and the amount of time it takes to get to y equals 0. So that's the process from A to B. And then the process to get from B to C, well, that's just delta y is equal to v times the amount of time. So this is h is equal to v sound times t. Now, here's the weird part. Neither one of these t's are the same as the value they gave us, and they're also not the same as each other. Now, when I have them written under headings, it's not that big a deal to have the same letter represent different things. But I need to relate these to each other. So when I want to relate this equation and this equation, I need to make sure that things that are different are distinct from each other. And my preferred method is subscripts. So I call this t sub 1, and I call this t sub 2. Now, it is the same height in both cases. The distance the rock falls is the same distance that the sound has to come back. So that's not something I have to subscript. I don't have to distinguish this height from that height. But I do have to distinguish this time from that time. Now, at this point, let's take a tally of what are our givens and what are our unknowns. I know G, I know the V of sound, so those aren't problems. But I have an unknown height, which is my goal of what I'm supposed to solve for. And I have an unknown T1 and an unknown T2. So I have 3 unknowns. I need to have 3 equations. Right here, I have 2 equations. So what's my third equation going to be? I haven't made use of the 2.93 seconds. So how is the 2.93 seconds related to my unknown variables? Yeah, it's the 2 times added together. So T1 plus T2 equals T total. So those three equations are the equations that you have to solve in order to get a final answer. Now, solving simultaneous equations is something that hopefully you've been practicing for a while. It's something that engineers definitely have to do fairly frequently. As a strategy, I usually try to solve it in the easiest way possible. I don't know whether that's mostly because I'm lazy or because I tend to be teaching and I want to demonstrate that what we're doing is not impossible to do. But I usually look for the easiest equation and solve for the easiest variable. So definitely, I would try to eliminate T2 as a variable because it looks easy to do. I can solve for T2 here and plug it into here. Now at the next stage, I need to eliminate another variable, and my choices are H and T1. And one of my philosophies is, unless I have to, I don't want to eliminate a variable that is squared. Because when I solve for it in another equation, I'm going to have to plug that in there and square it. And then it's going to blow up and get more complicated. So I would eliminate H as a variable next. So solve for H down here and plug it in over here. And then, actually, that's really easy to do because this already says H equals and this says H equals. So eliminating H as a variable is actually obscenely easy to do. And then you'll have a quadratic equation for T1, and you can solve for T1. Unfortunately, in this particular example, there's no way to get out of using the quadratic formula. With pure projectile motion, you can use the v² equation to avoid the quadratic formula, but this is not a pure constant acceleration situation. This is a two-stage process with different accelerations, so the best you can do is actually solve the simultaneous equations. And then once you know your T1, then you can plug it back in here and calculate H and get an answer. And that gets you the answer to part A. For part B, all you have to do is set T1 equal your total time. Part B says, let's say we ignore the travel time for the sound. So that's basically saying T2 is equal to 0. So we'll ignore all the equations with T2, and we'll just set T1 equal the given value and find H. And now we have a new H that's different from our old H. I want to distinguish them in some way, so I'll call it H2. Using the subscript 2 to me means by the second method, the second version of H. And they say, what is the percentage error introduced? So basically, how wrong is this value as compared to your previous value? Here's the trick that I learned by dealing with this particular question for a few semesters and then digging into the actual JavaScript code that WebAssign uses. you have to compare it to your original h as you typed it in for part A. So if you rounded your answer for part A, you have to compare this h2 to the rounded value that you typed into WebAssign, not to the fully accurate multi-decimal place value you still have in your calculator for when you did part A. Now, if you type in all those digits in part A, WebAssign will not mark you wrong. It'll be perfectly happy with that. I turned off the significant figures checking in WebAssign because I think it's crazy. So whatever you typed in for part A is what you use as your basis of comparison for finding the percent difference by the wrong method of part B. Hopefully that makes sense. All right. Does anybody have any other requests? Let me look at another important special case. So we did the case of coming to a stop. Now we'll do the case of starting from rest. So we're basically saying in this case that v initial is equal to 0. So that kind of fits into a lot of our equations. It fits into delta v is v final minus v initial. So that becomes delta v is equal to v final. V average is 1/2 of v initial plus v final. So that means v average is 1/2 of v final. It fits into delta x is v initial delta t plus 1/2 a delta t squared, because it becomes delta x is equal to just plain 1/2 a delta t squared. And it even fits into the v final squared equation, because that becomes v final squared is 2a delta x. So we actually kind of like situations where your object is starting from rest. It simplifies all the rest of our equations. And it's actually very symmetric with the process of coming to a stop. The only difference is when you're coming to a stop, it's v final that's equal to 0 and v initial is not equal to 0. And some of the equations will have some minus signs in them. Like the delta v will end up being negative v initial. The v average will end up being 1/2 of v initial without a minus sign, because there wasn't a minus sign in here to begin with. The delta x equation is kind of counterintuitively, or maybe it's not counterintuitive, it's just not obvious. The delta x equation turns into delta x is negative 1/2 at squared. So I think what I'm going to do is zoom out a tiny bit and do a VF equals 0 version of these. Delta V is minus VI. V average is 1/2 of VI. No minus sign. Delta X is minus 1/2 A delta T squared. And VI squared is minus 2A delta X. So that's what I mean by the equations are basically the same as if V initial is equal to 0, except there's some minus signs. So this one gets a minus sign because we have to kind of subtract VI over to the other side to isolate it. The delta X equation is the one that's kind of counterintuitive. And to figure that out, you can almost think of it like you're running time backwards. So the acceleration kind of has the opposite meaning. So being able to take our general kinematics equations and figure out, okay, I can ignore this term in the equation because it's equal to 0. So now my equation looks simpler. This is what it looks like now. Those are things that I did not put these on the equation sheet in general, but you should try to know them anyway. You should be able to look at the big general equation and say, okay, this is what it looks like when I make this thing 0. We have 15 more minutes. Let's do a quick example. A process of slowing down. So this is something that we do a lot. We drive down the highway. We have to slow down to drive on the access road. 20 meters per second is about 45-ish miles an hour. So that's about fast access road speed. Eventually, I suppose you have to slow down for the construction or the traffic light. But so this process of slowing, we can definitely say delta V is V final minus V initial is 20 minus 30 equals 25 meter. Wow, I'm jumping ahead in my head. Is negative 10 meters per second. We can definitely say the average is 1/2 of V initial plus V final is equal to 1/2 of 20 plus 30 is equal to 25 meter per second. Well, in order to know everything about this situation, we need to be given one more bit of information. So let's look at given A equals 5 meters per second squared. So if we are capable of an acceleration of 5 meters per second squared, then we can determine everything else about the situation. We can determine how much time it takes. We can determine how much distance it takes. So to make use of that, we would say delta V is A delta T. So this would be -10 is equal to -5 times delta T. So 2.0 seconds is equal to delta T. That's the easiest way to make use of the delta V information. And then you can say delta X is equal to V average. Delta T is equal to 25 times 2.0 is equal to 50.0 meters. So if you know everything about the velocities and then you know the acceleration, then you can very easily find the time and the displacement for that particular process. So now I want to do a different version of it. What if we don't have 50 meters to stop? What if we only have 40 meters to stop? How do we make use of that? Well, since we know everything about velocity, we can use delta X is equal to V average delta T. So this is 40 is equal to 25 delta. So delta T is equal to I can't divide in my head. $1.6. Seconds. And then we can use the delta V fact to find the acceleration. -10 over 1.6. Remember, our delta V is still -10. I'm still keeping the initial setup. So -6.25 meters per second squared. So compare these two situations. It takes a stronger acceleration to stop in a shorter distance. And then as a third version of the given delta T is equal to 1.5 seconds, we can make use of the velocities and the delta T fairly easy. A is delta V over delta T is -10 over 1.5 is something else. -6.67 meter per second squared. And then what else don't we know? We don't know delta X. X is average velocity times t. Average velocity was 25. Times 1.5 is equal to 37.5. meters. So my conclusion from that exercise is we started with a situation where we knew the velocities, the initial and the final velocity, which is basically the same thing as knowing the delta V and the V average. And then whether we were given the acceleration or the displacement or the time, that extra bit of information was very easy to use. And we didn't have to worry about solving quadratic equations. We didn't even have to solve simultaneous equations. So that's why if you're solving a constant acceleration process, try to find the velocities first. That's my strategy. Find all the velocity information first, and that opens things up to be able to find all the other stuff. Now, granted, if you're in a multi-stage process, sometimes that's not as easy to do, such as the dropping the rock down the well. And in that case, you may have to just work with equations with unknown variables, and you may have to solve simultaneous equations. But in general, if you can find a way to find the velocities numerically right from the beginning, you can end up solving the system without ever having to do simultaneous equations and without having to do a quadratic formula. All right, so on Monday, we are going to talk about multi-directional motion. We're going to talk about vectors and vector components. We're going to have to do a little bit of geometric trigonometry, that is applying the definitions of sine, cosine, and tangent, and the Pythagorean theorem. And we'll do a little bit of projectile motion. So come in Monday ready to use basic trigonometry. Review it if you haven't done it in a while. And then we'll do those things Monday and Tuesday. By Wednesday, you want to have worked on homework 2, because on Wednesday, I want to be able to review and go over example questions to get you ready for the test on Thursday. Yes, it's fast. It's summertime.